Hello, my name is Xiyao Wang. I am currently a PhD student at INRIA, France and the University of Paris-Saclay. It is a pleasure for me to share our joint work with Lonni Besançon, David Rousseau, Mickael Sereno, Mehdi Ammi, and Tobias Isenberg about towards understanding of augmented reality extensions for existing 3D data analysis tools. The main motivation of this project is that previous studies showed that immersive visualization with stereoscopic views help understand 3D datasets, and many of them have been created during the past years, ranging from large environments like a cave system to smaller ones like head-mounted virtual reality or 3D glasses. However, even though the benefits of visual immersion have been demonstrated by many studies, for example, there are controlled experiments proving that users can understand the biological structure easier in immersive systems than a normal screen. Few of them have been practically integrated into scientific usage. We thus want to investigate a practical way to bring immersive visualization to their daily workflows, how to choose the appropriate devices, and how to design the good interaction techniques. For this project, we are working with domain experts in particle physics. This is an example of particle collisions. In general, one event is very large and can contain more than 10,000 particle trajectories. With traditional visualization on screen, those traces overlap each other and lose spatial direction. It is thus hard to understand how particles travel in space, so they have interest in using immersive environments to explore their data. According to our discussions with physicists, they do not only rely on visualization to understand the data. A common approach is that they first use some statistical tools to analyze the data, to find their regions of interest, and then, with visualization, they try to understand the event. Very often, they need to consistently switch between the analysis software and visualization tools to accomplish data exploration tasks. There are some important elements in this process. The first is that traditional analysis tools heavily rely on script typing and precise parameter adjustment, where mouse and keyboard are still demanded. Secondly, 2D plots like histograms and texts are still very important. Thirdly, they need efficient 3D visualization. Based on these considerations, we investigate an AR extension to existing data analysis tools. In this project, we use the Microsoft HoloLens. We investigate the scenario where users sit in their office and work on data. The general design comes from the scenario where experts use two screens. They use mouse to interact with both screens, and the cursor can go from one to another. Then, one screen is replaced by the HoloLens. In this study, we keep the same interaction on the PC and on the HoloLens. We still use mouse to control both spaces, and the cursor can go from one to another. Although there are previous work illustrating different techniques of bringing immersion to existing workflows with different choices, we focused on different aspects. For example, we want users to be able to see both views at the same time rather than forcing them with only one. We also want to provide a uniform interaction experience to avoid frequent change of input devices. We detailed our choices and the differences in our paper. We show a part of our implementation here. We use the similar user interfaces on both sides. The left side is on the PC and the right side is on the HoloLens. Users can perform any functions on any side. Everything can be done with the PC or with the HoloLens. Based on our discussions with physicists, we implemented some basic functions to explore their datasets. We only show a very short concept here. This is an example where we can highlight or filter particles using a histogram. In this study, the two species can be synchronized and also can be treated separately and synchronized on request. As mentioned, both sides have similar interfaces, and any functions can be performed on the PC or on the HoloLens using the mouse cursor. This is another example that users can select specific particles using a lasso tool in AR spaces. This function can also be performed on the PC as mentioned above, and the results can be synchronized directly or just keep on the one side and synchronize on request. Then, to understand how experts would want to use such a link view design, to investigate if desktop interaction can be well supported in AR, and to gather any other possible comments for future design, we performed an observational study with 7 physicists from CERN. This study was pre-registered to follow the best practices in experiment design, and the pre-registration and data are available online to follow open science principles. The experiment is composed of 3 main parts. First is a tutorial and explanation, where the experimenter introduces the system and supported functions. And then a free exploration phase. We ask participants to freely explore a simulated dataset with all possible functions. During this process, the experimenter stayed with the participants, took notes, and helped them when needed. We also encourage the participants to ask questions and think aloud. At last, we conducted a semi-guided interview to get their comments. During the last part, we asked participants many open questions and several like-scale ratings to get their general feedback and envision a future design. We reported and discussed the complete results in our paper. We only briefly summarize some of the insights here. For example, all participants like the hybrid setting, and 5 out of 7 preferred a balanced interface. In general, experts had no difficulties using such a hybrid setting. They agreed that this is feasible and useful. Both sides have their advantages that can benefit data exploration. For example, expert is familiar with the PC and can understand easily the results from their traditional tools. And the PC also facilitates the precise interaction using mouse and keyboard. While the AR part largely favors the spatial understanding, the additional depth clue makes the 3D trajectories very evident, and the spatial arrangements between different elements are also much clearer than a normal screen. In addition to their familiar view on PC, the large canvas in AR space facilitates the multiple view analysis that are often involved in their workflow. It would then be useful to flexibly adjust views in space. However, despite the technical issues of synchronizing the mouse movement between the PC and the HoloLens, how to use the mouse cursor in 3D spaces still remains further investigation. Apart from that, walking around is seen as a great feature of using VR compared to VR systems that are tied with the PC. One participant particularly mentioned that he noticed the advantages of stereoscopy once he stands up and walks around. This is also seen as the main differences of the AR compared to a normal screen. Then, it would be a good idea to let users to define the link between the two spaces, depending on whether they want to explore the data or to compare different states. In conclusion, we presented a study to investigate how particle physicists want to work with a hybrid setting to extend their current analysis tools with immersive visualization. In general, they agree that such setting is feasible and can help their data understanding. We gathered comments and discussed some guidelines for a possible future improvement. While we are focusing on particle physics, our results do not limit to this area. Other settings like a VR room and other domains dealing with studio data can also benefit from our results. There are many features that worth to be further explored in the future. For example, we have mainly two things to continue for this project. If you are interested, please contact us. First thing is to investigate both intuitive and precise interaction, how to appropriately extend the mouse to AR spaces, and how to combine other inputs seamlessly into the hybrid setting. Then, we also want to apply this setting to a more realistic scientific scenarios. One current project is that we want to use our setting to compare different algorithms of reconstructing the particle trajectories from measured data. This is the end of my talk. Thank you for your listening. If you have any questions, please contact us, and you can read our paper from the QR code.